Hello. A few months ago I decided to try and build a little robot arm like this, kind of like a industrial robot that you see in factories, like they just sort of move things around, pick them up and manipulate things. And the main reason that I decided to do this was because earlier this year I built a CNC machine, just a small desktop sized one, and I hadn't really used it as much as I thought I would, but this project here seemed like the perfect thing to put it through its paces and use it a lot, because it requires lots of complicated, precise parts, and they're also not too big, at least for this model that I'm looking at here. So this is from this point here to that point there is roughly 20 centimeters or so, so that'll give you an idea of the size. And my goals for this were to use this to try and just to have fun, basically, and also to write some software or Arduino code to control stepper motors and have everything controlled by my software, basically, was the other reason to try and do it. And the scale, like I said, is pretty small. I didn't want anything too big and clunky. I wanted it to be something that I could just sit on my desk in front of me and work on. So that's why we have ended up with this. And you can see this down here. This is a NEMA 17 stepper motor, so that'll give you an idea of the scale as well if you are familiar with those motors. It's not a very big one. You see them in 3D printers and so on. And the restrictions for construction were that I wanted to be able to make it out of material that I could cut on my CNC machine, of course, so that limits me to stuff like plywood, FR4, and as I also discovered later on, acrylic, which is very good. I love acrylic. It's very easy and fun to machine. And I wanted to get most of the parts from places like Banggood and Hobby King that don't cost too much. I didn't want to have to outsource any of it to professional CNC machinists where I'd have to pay lots of money and things like that. So I wanted to keep it to the range of things that I could pretty much do myself here at home. And what we see here, another thing that I thought I might do is actually make some of the parts out of aluminium. That quickly fell by the wayside once I realized how slow my CNC machine is to make things out of aluminium. But one reason why we have these sort of long, thin, flat pieces here is because I was thinking to make these pieces out of aluminium bar that you can buy from Bunnings or Mitre 10 here in New Zealand, and so that limited me to a 5 centimeter width if I was going to be using those pieces. Now that I'm using mostly acrylic, this plan has changed quite a bit, but let's have, have a look through and see how it works. So it's going to be a 6-axis arm, which makes things quite complicated, as I found out, and that's why I've gone through so many different iterations of changing this and tweaking this and trying to get it to work properly. And also, as I discovered pretty early on, the distribution of weight around the arm is very important as well. So if anybody's familiar with these, you might actually be looking at this already and seeing why that's not going to work. But I'll show you later on some pieces. At some points I stopped my SketchUp planning and I sat down with the CAD program, drew out some plans and actually made some stuff and tried it out, and then thought, oh crap, that's not going to work. So I'll show you some of those as we go along. I originally thought that I might make this into a nice video series for YouTube, and have like all the parts nicely explained, but it just became such a long project, and quite frankly, doing stuff for YouTube, making videos, really slows you down. So I just did things as I felt like doing them and recorded a little bit of video along the way. So what we're going to end up with for this series is some random clips just at the times that I felt like recording, and I'm just going to throw them all together. They will at least be in chronological order, but they're not going to be very nicely presented as they could be. Anyway, I've waffled for quite a while without really looking at this, so let's dive in a bit. These pieces here are linear rail mounts, the same as I have on my CNC machine. This is, I think, a 10 or an 8mm bar, and the gears in here I'm planning to make, or I have made a lot of them already, with acrylic, and I think I showed this in one of my earlier videos about the CNC machine. You can use a drill to make the little grooves in the gears and then cut around the outside of it after that with a normal end mill, and they work out pretty nice, and you can make any size gear you like, well, within the range of your machine and what raw material you'll have available. But you can see that these two motors here, one of them will be lifting the arm up and down, and it may not be very clear from this, but this is a compound gear, so these two pieces are joined together and they are freely rotating on this axle. And so this belt, there's going to be belts. I'm using GT2 belts. Turn out to be a little bit small for some parts of it, but I think they will suffice. So there's going to be a belt coming from here to here, and then a belt coming from there up to here to rotate this this piece here, which I'll call the elbow, I think, for most of the rest of the videos. And then in here, or below here, we have another motor which is going to be turning this piece. I've taken some shortcuts with my drawing of these things. This is supposed to be a larger GT2 pulley wheel here. And that's going to be turning this shaft through the middle, which is supported by two very, very heavy pillow blocks, and then some more heavy pieces of linear rail mounts there. And then this stepper motor would be connected from here to the front piece there with a belt to tip this bit up and down, and then finally the sixth axis would be directly from the gripper or the end effector mounted on this stepper motor shaft there. So that's a 6 axis. Oh, sorry, we didn't look at this one down the bottom. So this piece I actually also showed in one of my previous videos too. This is a slew bearing, or like a Lazy Susan kind of a bearing that I have made a version of out of acrylic, but I'm going to have to make another one because I did not put any gear teeth around the edge of it. So in the final version we'd have a pulley coming from this stepper motor, and it would be turning the upper piece of this gear with a, it would be gear teeth all the way around, and hopefully that should be enough of a gearing down to give it enough torque to move it around properly. So I actually did get to this point, and then I constructed just this top portion of it here. So I think I'll show you that now, and then we'll come back and look at what I changed and decided to modify after that. So this is my first design, part of the first design. This is the upper section of the arm, and as I put this together I began to become more and more aware that it's just never going to work. Way too heavy, basically, is the main problem. Not only heavy overall, it's 760 grams just like this, just with plywood, never mind aluminium, just plywood, 760 grams. But also that the problem is that a lot of the weight is over on one side, because these two motors are to the left. As we look at it here, they're to the left of this point, which is going to be the swivel point at the top of the arm. And not only does it require quite a lot of strength here, so the motor needs to be quite strong, but it also relies on a lot of strength. Like, this belt has to grip very, very well, and I just didn't really trust it. Plus, I found that these small motors are very weak. They are, just considering how much smaller they are than those other NEMA 17 motors, I thought just scaling them down, they'd be that strength scaled down. But it seems like the strength of the motors doesn't scale down with the size. It gets way, way weaker as they scale down, like on a sort of a logarithmic curve or something like that, maybe, or exponential curve perhaps. So yeah, this motor, this is another problem with this design. I have a motor on the swiveling point there, so in order just to stay still at that position, it has to hold the weight of the motor up, and it can't do it. It's off at the moment. But even when it's not on, oh no, sorry, when the power to the motor is on, it actually can hold that. That's okay. But it's not very strong, so if you put a little bit of weight out on this end, if you tried to pick something up that was a little bit of mass to it, it might be, again, having trouble. And the weight problem, apart from coming from the stepper motors being over here, I also have these very heavy aluminium clamps on this front section, and in here this very heavy bearing over there, and also this is probably the heaviest or most needlessly heavy part of the whole thing. I would cut that here, of course, but still, this steel rod, it's one of the bearing rods like I used in my CNC machine, that's also very heavy as well. So the idea is that this piece would turn like turn like that for one axis. Trouble is when it gets to about here, the weight of that motor being up on the top sort of tends to tip it down. Anyway, so it's not going to work. It's never going to work. But I'm just about to take it apart but I thought I would show you what it looked like before I take it apart. So let's have a little look at it trying to do some movements. And I mean, it works, but it's just borderline, especially with this one here. I can pretty easily move that one. The motor is actually this motor is actually turning as well. So that's three motors coordinated using my stepper motor control system. You can't see that very well from the top. Let's have a look at it from under here. So you can sort of see all of these three motors working together. So it just moves them two and then one by itself, and then puts all three of them back to where they started. And you can see every time I reset the Arduino, the power going off to this motor, or that motor, makes the front motor just sort of droop down when it's no longer being held steady, like that. So that was a fail, and I'm about to take it apart and maybe do something else. Another thing I learned from this, or what I was able to experiment with, is how far you can take the distance between these two plates and still expect to have some sort of rigidity. And I imagine this wouldn't change too much with other materials. Plywood, of course, is a little bit soft, so when you try and do movements like this, I'm just sort of moving one plate front to back relative to the other one. And plywood, of course, lets this piece here sort of squash into the wood, so you can do that a bit easier, but still it gives me an idea that probably this kind of distance is going to need more than just sort of a couple of standoffs at the front and a couple at the back. And then when we get over here, you can see it's sort of stretchy there, although I don't have any supports around this axle here, which kind of makes it worse. But anyway, it was useful to do this construction. As far as cutting the plywood and getting everything in the right place goes, that went pretty well. I had to move this hole or make an extra just to, try things out. But overall, I'm getting pretty good at doing the CNC design and making the cuts in the right place, so that this piece that I cut to fit into this other piece will actually fit in when I try and do it physically, like this here, for example. That construction is no longer any cause for concern when I'm sitting down to design something. It usually works first pop. So that plan was never really going to work, and if I had have thought about it a little bit more carefully before actually making something, I probably would have realized that. But it doesn't hurt to take a break from staring at the computer screen for a while and actually make something. And when you're holding it in your hand like that, it really drives home, what it's actually going to be like. There's no substitute for actually having a physical object to touch and look at and stuff. So anyway, that led me to investigate how real industrial robots are managing this problem of having the weight. Essentially, you want to have the weight balanced around this point here, so that the motor doesn't need to really be continuously lifting this section, because the back and the front will be the same weight. So it just needs to sort of be moving them rather than lifting, so there's a counterbalance at the back. And I looked into that a little bit, and I came across this video where a couple of guys, I think they're trying to figure out what I'm trying to figure out, and this is a proper industrial robot, and you can see that at the back of the elbow there are three motors. So all of the three motors that move the wrist are way at the back of the elbow, and they are turning some concentric shafts, I think, and those shafts are turning belts at the other end, and they're sort of routed around the outside of the arm and back in again to turn the final three axes there. So that gave me an idea, and here it is. Even though I thought I might be starting in on another pipe dream again, I thought it can't hurt to just sketch it up and see how it's going to turn out. And so this is the idea here. Some of the carbon fiber tubes that I have for quadcopter parts and so on are very, very strong and rigid, and they would make a pretty good final arm section as long as they could be mounted on some bearings and stuff. And you could actually put other tubes inside them, and I bought some aluminium tubes in slightly varying sizes and some bearings that I could mount them all nicely and do this with. And the nice point about this is that you can see I've detached this here. It gives you quite a bit of freedom in this length. You can make it basically whatever length you like. Just cut the pipe to your desired length. It's quite nice. What's not nice is how you have to arrange this. So you've got your 3 motors at the back. That's how I would have had to arrange them, or something like that, if I actually did this. This part wasn't really a problem. The problem that made me give up on this is the complexity of this part. So I would have had to have, for the last 2 axes, these 2 pieces would need to turn, and then, well, it's basically what we just saw in that YouTube video, but you'd need a belt that came here and then turned 90 degrees and went around there, and another one. And this whole front section would be getting quite large and goofy looking, and it's just a problem of making things in this small scale is that all the parts, like the size of the belt relative to the size of the robot itself, starts to become quite large. And yeah, I just didn't really feel like designing this out any further, so I abandoned that one at that point. But I did like the idea of using a tube for this section, so my next attempt, or next variation, was this one. And the bottom is all the same, by the way, in these, but I've kept the carbon fiber tube for this section, except that it's only one tube now. There's no other tubes inside it. But in order to get at least one motor, at least 2 motors at the back here, what I've done is I decided to buy a smaller motor to keep this bit at the front. It was just so convenient to have this axis directly on the motor there. You don't get any gearing down, so you're not going to get any stronger torque or lower speed. But at this point, you don't actually need too much strength, or you don't need any gearing down really too much, because the movement that this motor does is going to be the final movement. Whereas, for example, this one down here, every degree that this motor moves is moving this point a lot. So if I suppose that this point here moves 1 millimeter forwards, this little edge of the arm moves 1 millimeter forwards, in this arrangement of joints, that's going to move this point about 6 millimeters forwards, for example. I'm just giving rough guesses, but the relative movement is going to be much more as that movement translates all through these joints. But at this point, you don't have that problem, because you don't have any further joints after this one. Hope that makes sense. So I decided to go with one of these little stepper motors on the final joint, and given that it's smaller than the 2 at the back, so now we're talking about NEMA 8. This is a NEMA 8 size motor. The 2 at the back are NEMA 11s. So they're a fair bit bigger, and they do quite nicely balance the one at the front, as I discovered when I actually built this up. So the arrangement I've come to here, I kind of like this one because it makes the motors a little bit symmetrical. So another goal that I had when I was thinking about how this was going to look is try and make it look kind of neat. So if it can look roughly symmetrical like that at the back, I know I shouldn't be thinking about that. I should just be thinking about how it's going to function. But anyway, I like the way this one looks. So I've just taken this plate away on that side so we can see what it's like inside. So we've got one motor horizontally above there, and it's going to be turning that carbon fiber tube, which is riding on a bearing here and a bearing there, and it's being turned by a belt from here to there. Now the slightly pipe dream element of this design is that in order to get the movement from this motor to the front, I decided to try running a belt inside this tube. Now this is only a 12 millimeter carbon fiber tube, so it's quite small diameter, and in order to get the belt in there properly, it needed a couple of kind of rollers to make it pinch in a little bit there. And then at the front, another couple of rollers would keep it pinched in there as the belt goes into the pipe there, and then the belt would just wrap around this piece here, which is connected to that bit on there, and it would turn it and everything would be great. So I kind of like the way this was heading, so at this point I again made a prototype, so let's have a look at that.